This is the geology of the Cayman Islands, evolution of complex carbonate successions on isolated oceanic islands. This book came out in November last year. It's a unique and thorough record of the specific geological research that Dr. Jones and his colleagues have carried out in the Cayman Islands, and it is based on extensive database of fieldwork and laboratory analysis. The book summarizes the current state of knowledge regarding the geology of the Cayman Islands, and you can get it at the National Trust, Books and Books, Book Nook, or, like a lot of people do, you go on Amazon.com where you can buy anything you want. Geology Week was organized for the first time in 2013. During this week, Dr. Jones provides geology education at high schools for high school teachers, students, and professionals in the Cayman Islands. Due to its success, we have decided to organize Geology Week again this year. With that, I pass you on to Dr. Jones.
Good evening. Thank you for taking the time to come and listen to it. I hope I can provide you with information, some insights into various aspects of the Cayman Islands. You may wonder about the title, Geology and Water, Cayman Islands, and you'll see that on here there's a picture of water, there's a picture of the rock, there's a glass of water that you may drink every day. So what is the connection? These rocks here, limestones and dollarstones, they formed in the oceanic waters. A long time ago, when these were all submerged, the water that you drink today comes out of rocks like this. So there is a link there. And that's the one I'm going to explore tonight, and hopefully can demonstrate to you the problems and issues in trying to get water out and process it so that the Water Authority can deal with it. You may wonder why a geologist who's based in Western Canada would come down to the Caribbean to do research. Obvious answer, it's warm down here. It's very cold in Alberta during the winter when we can go to minus 35 and minus 40 degrees. But there is actually a practical reason. On this diagram here, I'm showing you a cross-section, a schematic subsurface cross-section through Alberta. Notice here the Leduc Reef. This reef is actually not far from where I live. You can't see it, it's down in the ground. But these reefs, formed of limestones and dollarstones, that's where the oil and gas occurs. So if we have knowledge of the rocks there, we can retrieve it. How do we get the knowledge? My story is I come to the Caribbean, not because it's warm, I come here to do work, so it will help me understand the rocks that are here and help in the oil and gas exploration. And that's the reason a lot of my students, my PhD students, my MSc students have come here, and they've gone on very successful careers, both in industry and in academic venues. So there is a reason. These Devonian reefs in Alberta, about 350 million years old or so, give or take, got a lot of similarities to what you see around the Cayman Islands. These reefs are formed of complex frameworks produced by corals, stromatoporoids, and various other animals. Stromatoporoids no longer exist. They were common in the Devonian. Similar to corals, similar growth patterns. Believe it or not, if we'd been in Alberta at that time, these reefs grew in tropical seas. Exactly the same as what you see here. And the reefs are formed of carbonates, CaCO3 sediment. When we use the term carbonate, this is what we're referring to, the calcium carbonate, which is the prime building block of these rocks. In order to develop in these fields, I can't claim to do this. This takes oil companies with massive resources. Geological exploration, mapping, interpretation of carbonate sediments, knowledge of porosity and permeability in the constituent rocks. All of these things that apply to those reefs are things that we can deal with on this island, and as it turns out, helps with the water resources. We use the same principle. Water, gas, oil, it's all the same. I show you this map because you saw on the previous diagram that Leduc Reef sort of sticking up and surrounded and buried in the shales. You say, well, that's kind of strange. But look here, there's Grand Cayman. You've got water depths in here to 27,000 feet. Imagine that we fill this up with mud. Mud forms shale. There's the Grand Cayman formed of limestones. You'd have exactly the same thing. So that's the connection. The set in here, and obviously we're going to talk about Grand Cayman, Lower Cayman, and Cayman Brac, these three small islands. Tremendous water depths to the south, as I say, up to 27,000 feet or more, and fairly deep water to the north. They are truly isolated. On these islands, at first glance, it's easy. There are two rock types. There's limestone, which is calcium carbonate, CaCO3. There is dolostone, which is formed of dolomite, which is a calcium magnesium carbonate, CaMgCO3 twice. These are not the best pictures that I've ever had for these rocks. But if I was to give you a piece of limestone in your left hand and a piece of dolostone in your right hand and just gave you the rocks, you probably wouldn't be able to tell them apart. They are so similar. And this is why you often see a geologist carrying a little bottle that contains 10% HCl in it, because if we squirt that and this, we get a reaction, it's limestone. If we squirt it on here and there's no reaction, that's dolostone. So it's a simple test, in most cases. If you look back at the history of the development of geological knowledge for the islands, the first geology map that was produced was in 1926 by Matley. Matley was a member of the British government that was based in Jamaica. And in about 1920, I think 1919, 1920, he was either sent or wanted to come. He sailed over to Cayman, he landed here. He then sailed around and got to Georgetown. He spent 4 days on the island, just 4 days. And during that time, he came from Georgetown to about the midway point here. There was some trackways that he could go. He then went by horse from here to the east end here, got in a boat, sailed around the island there, sailed across North Sound back to Georgetown. Remember where we are, 1926. There's no air photographs, there's no satellite imagery, there's no maps. And yet he produces this map where he shows two sequences of rock. This sequence shown in cross hatch, what he called the bluff limestone, and this here, the Ironshore Formation. And I want you to keep this map visualized in your head. The next map that was produced in 1973. Look at the time gap. This is by Brunt et al. Look at the similarity. This symbol here is the limestones. There is the Pleistocene rocks. Look at the similarity from here to here. I still don't understand how Matley managed to produce that map. It baffles me. If we go to a more recent map, such as the one we've produced, again, notice the similarity to Matley's original map. We haven't been able to improve on it. Well, we've improved on it. We've got satellite images, we've got air photos, but working against us is all the undergrowth and mangrove sort of coating. So that doesn't help. We have changed the terminology of the sequences here, so that we have the Brac Formation, Cayman Formation, Pedro Castle Formation, Ironshore Formation. We do not see the Brac Formation on Grand Cayman. Sometimes we encounter it when we're drilling. It's typically about 350 to 400 feet below the surface. We find Cayman Formation over most of the east end of the island, Pedro Castle Formation just in this area around Pedro Castle, and then the Ironshore Formation shown in level in yellow covering the rest of the island. Fundamentally, the geology is, according to the map, is fairly simple and straightforward. If we go to Cayman Brack, situation is a little bit different. During its history, Cayman Brack, Grand Cayman is sat like that, horizontal. It may have gone up and down a bit. Cayman Brack has been tilted, such that the east end of the island has gone up, the west end of the island has gone down. And because of that, we can actually see the Brack Formation at the extreme eastern end of the island. You may ask, why is it not shown on that map? The reason is, we can only see it in the cliff faces. So you can only see it there, we can't map it vertically. It's that simple. And then as we look at these, the Cayman Formation dips down to the west, we get the Pedro Castle Formation at the western end, and we get the Iron Shore Formation forming around here. Thankfully, on Cayman Brack, we get great exposures of the rock. One of the problems we're always fighting with on Grand Cayman is there's not a lot of exposure. In order for me to get to the explanation of water and how it's produced, I've got to show you and give you a little bit more information about each of these formations. So I am going to have to delve a little bit more into the geological terminology. I'm going to try to avoid as much jargon as possible and keep it simple and straightforward. So the Brack Formation is formed of limestones and dollostones. Lots of fossils in it, clamshells, bivalves, foraminifera, red algae, and gastropods. Cayman Formation, which overlies it, basically all dollostone, although there are some locations we found on the east end of Grand Cayman where it is limestone, strangely. Again, lots of fossils, not well preserved, as you're going to see. Then the Pedro Castle Formation, which is a mixture of dollostones and limestones, lots of fossils again, not particularly well preserved. Iron Shore Formation, limestone, full of corals and gastropods and bivalves, beautifully preserved. Some of these rocks, these corals you pull out, 125,000 years old, they've still got their original aragonite skeleton. Aragonite is a very unstable form of calcium carbonate. It will change, it will dissolve very quickly. But for some reason, it's being preserved within the iron shore. Beautiful. You can see all the skeletal textures of the corals and everything else. Okay, so what do these formations look like when we're looking at them? This is on the east end of Cayman Brack on the south coast. And here, these massive rocks like this. It took us a long time to recognize some of these features because these are so massive, you know, there's lines going all over the place. We finally realized there's a continuous line that comes through here. You can see it quite clearly. This is the Brack Formation. There's the Cayman Formation. Notice the caves that you've got here, the ceilings are flat. And they're flat because they're at the boundary between the two formations. One of the troubles we have in dealing with geology is that obviously, if you look at that sequence of rocks, you can appreciate that that's taken a long time to accumulate. And if I was then to ask you a question of where is the maximum time representation on that slide, you'd probably tell me quite rocks. Wrong. The maximum length of time evidence on that slide is this line. It's a couple of million years. And that's because the island's been exposed, it's been weathered, and what you're seeing there is the old weathered surface of an island. So this is what causes problems in geology. You can't just do a direct correlation with time. If you look at this at first, I'm quite used to looking at these. It took us a while to get our head around it because everything is negative. So here, for example, all these holes, You say, well, what are they? But you notice if you look at these holes carefully, they're similar in shape, they're similar in size. These are actually foraminifera. Here, there's a cross-section through a bivalve shell, and here. But you notice there's no shell material in here. And that's because these critters, when they were alive, the shells were formed of aragonite. It got dissolved. So you're left purely with the molds. Great for porosity, if you're looking for reservoirs. Not very good for the paleontologists that are trying to identify the species, because you've got no features. And this is a common theme that you see throughout the geological successions of the Cayman Islands. In the Cayman Formation, shown here in Antietam Road and Cayman Brack, fairly featureless. It's white, it's hard, it's finely crystalline. I've just got my regular small geology hammer here. Sometimes you need sledgehammers to break this stuff. It's so hard. Again, you see the holes in the rock here. That's where branching corals used to exist. And again, formed of aragonite, they're dissolved, they create the porosity. Some of these other examples, but if you're looking at this formation, you've got to get used to looking at the fossils in a reverse sense. You're not looking at the skeleton of the fossil, you're looking from the infill of the fossil. So imagine that you took a fossil and you poured plaster of Paris on it, and then took the skeleton away, you'd be left with the mold, and that's what you're seeing here. So here that's a coral. You can just see the outer skin of the coral. These indentations tell us what it is. This is a solitary coral. You can see at first glance, you say, oh, that's easy, they're the septa. No, the septa are the holes, those lines with nothing in. There's a gastropod shell, but it's the interior of the gastropod shell. There is a bivalve or a clam shell. You see the gap around it? That gap is where the shell used to be. Now, why would we worry about this? Well, we worry about it because all of this is great porosity. This is where the fluids would fit. If I was looking at the rocks in Alberta, this would be where the oil and gas would be. Here now in Cayman, this is where a lot of the water sits in these types of cavities. If we come to Pedro Castle area here on Grand Cayman, there is the Cayman Formation, there's the Pedro Castle Formation. You notice a beautiful straight line here. It gives you the impression that the land surface was very flat, and I'm going to show you that's not the case. Unfortunately, now in the quarry, it is so overgrown, we can't even get in to look at this face anymore. And it's also on private land, so. But I'll add that when it's on private land, we always get permission to go in. Again, in this formation, these are corals that you see here and here. They don't look great, but I take my word for the coral. All of these things indicate that these deposits were laid down in tropical waters, much like we have today. The Iron Shore Formation, this is showing a picture here on the northwest coast of Grand Cayman. If you're a fossil hunter, this is where you go. Beautifully preserved. If you look at this picture here, just about the whole thing is jam-packed with corals. They're still formed of aragonite. You can see their original structures. We have on rare occasion in the bivalve shells, these rocks are 125,000 years old. We've actually found some bivalve shells with the original color of the shell. It's amazing, and it's such a contrast to those older rocks. So hopefully with that brief introduction, you now can fully understand the geology of the islands. And here, I'm going to put you to work. Because here, this is a piece of core that we would typically take. You can see the features in here. Somebody tell me what you see. Limestone or dolostone, you see holes. Great. Geologist looks at that, we see money. And the reason we see money, that's where the oil is, that's where the gas is, that's where minerals are, and here on Cayman, that's where the water is. You've got to get used to looking at rocks in a different way. They're not just a hard piece of rock, they're important. So, I've had to introduce this in this manner so I can transition into talking about water, and in particular water production by the Water Authority, given that most of you are drinking water that's being produced by the authority on a daily basis. And the problem here is that as the population of the islands has increased, so the demand for water increases. And if you go back in time, I'm not saying these are accurate figures, these are the best figures I can find. So 1802, less than 1,000 people. 1966, 8,400. 2006, 52,200. 2021, 68,656. Population is increasing at growing rates. Fine. But what that means is you're putting increased demand for water. So as you can see here, the amount of cubic water that's needed each year is steadily increased, both on Grand Cayman and Cayman Brac. If you're faced with that, then there are issues and problems. Now, on Grand Cayman, there are three main freshwater lenses. There's the Lower Valley, North Side lens, and the East End lens. There used to be a lot of small lenses on the Western Peninsula. They got destroyed because over abstraction, and I'll explain what that means in a minute, or the pollution. What you have to realize is that these water lenses, they're underground, but they are floating on top of rocks that are filled with seawater. And that's the picture I want you to have in your head. Fresh water, lower density, it floats on the seawater. So if you over-abstract from these, if you take too much fresh water out, the seawater will come up and replace it. And because fresh water is lighter, you can never push that back down again. So once it's come up, you've ruined the lens. Also, with these limited, in relative terms, limited size of these lenses, it's become increasingly difficult to supply fresh water for everybody on the island. It's complex because if you look at rainfall, for example, the wettest area of the island is down here, and less rainfall as you go that way. I've shown the graph is simply showing the variable amount of rain each year. Everything changes, it's not predictable. Don't worry about the details there. Just look at it and see, yeah, the graphs are showing it's all over the place in different years. So it's hard to predict what you're going to do with it. On Cayman Brac, you've got Tibbetts Turn water lens and some small water lenses here. This has not been developed. Some people use the water, but other than that, you haven't got any fresh water, or you've got limited amounts. To try and help you visualize what a water lens looks like, people have this idea there's a lake underground. It's not, although I'm going to show you a slide which contradicts that. In geology, we always have things that contradict one another. But basically, what you've got are the bedrock, the limestones or the dollostones, and then you've got fractures, you've got caves, joint systems, and then the fresh water sits in a lens like this. In 99% cases, 99.9% of cases, it's not a lake. It's just all the water is dispersed through the rock. The exception here is on Grand Cayman. If you go into the Crystal Cave complex and you go into one of the caves, you come across this lake. This is fresh water. This is the surface of the north side lens. So as I said, there's always exceptions. So there, but don't think about that as being normal. It's actually abnormal. It's just a fluke of nature. So I wind back and show my age even more. In 1993, I got a request from the Water Authority saying that they wanted to install a reverse osmosis water plant at Lower Valley. Could I help with the geology? Now, reverse osmosis, what it means is you take seawater, you don't touch the fresh water, you take seawater, you treat it, you can produce fresh water from it. There is a catch to this. You cannot convert all of the seawater to fresh water. You can convert for per gallon, it's about 40% fresh water, and then you get 60% of more saline water when it's at the end. So these are things you have to worry about. Along with this invitation, they needed a well from which you could abstract 10,000 cubic meters of seawater each day, could not damage the existing freshwater lens, cannot damage any of the vegetation on the surrounding land, and from that 10,000 cubic meters of seawater, you can produce 4,000 cubic meters of fresh water, and then you're going to produce 6,000 cubic meters of more saline water. And you'd say, well, so what? Just throw it back in the ocean. If you did that around Grand Cayman, you'd kill every coral reef around it. Corals are so sensitive to salinity ranges that even if you increase the salinity range a little bit, you're going to kill it. So yes, you could pump this back in the open ocean, but you're going to kill the corals, kill the tourist industry, dive industry, and everything else. So you have to find a way of getting rid of that brine in a manner that's going to damage the environment. So these four criteria are actually, when you think about it, you look at it first and go, ah, sounds reasonable. And the more you think about it, you're going, we got problems. So let me show you what we did. Oh, and the disposal there. Oops. So on these, you cannot extract, just to summarize, you cannot extract fresh water from the lens at a rate that exceeds its replenishment. And it's extremely difficult, that freshwater lens, to be restored once it's been destroyed due to over-abstraction. Just to emphasize that point. So since 1998, in terms of when the plant first came into producing water, the rates have occurred. So for most years, it's about 2 million cubic meters per year. Sometimes the highest is 3 million, about 3.2 million cubic meters in 1 year. If you're having trouble visualizing that, if you're going to take out 3 million gallons of water here and fill the school bus, I don't know why you want to do it, but I'm trying to put it into a context that you can understand, you need 120,000 school buses. Just to give you an idea of the volumes of water. It's so easy to talk about 1 million gallons of water, and you can't visualize it, but I hope that will help. So what we did at Lower Valley, brought a drilling rig in, drilled, produced all this core that you see here. The core was sent to me in Alberta, and we did various testing on it to find out what the properties of that core were. Two of the most important properties that we have to assess and deal with, one is porosity. Now, porosity is a measure of the voids of all size in a rock sample. It's expressed as a percentage of the rock. So if I say it's got 10% porosity, it means 10% of that rock are just holes filled with air. Theoretical maximum is about 49.5%. If you go to 51%, there's nothing to hold it together. It's just going to collapse. And believe it or not, some of the highest porosity I've seen are from rocks on this island. I've got examples with 48% porosity. And you handle it very carefully. Permeability is a little bit more difficult to understand. Permeability is a measure of the ability of a rock to transmit a fluid through it. So what I want you to imagine is you've got a rock and you're measuring the rate and the ability of that rock to transmit the fluid. In other words, can that water go through the rock or can it not? We typically measure three measurements: K max in the horizontal direction. K max, K is a short term for permeability. Max means maximum permeability. And then once they've found the maximum, we rotate the core 90 degrees and measure the horizontal permeability again. And then we also measure the vertical permeability. So we've got lots of data. You may wonder, why do I show a piece of cheese in a lecture on geology? I haven't quite gone crazy yet, but I want to give you a visual impression by what we mean. And you notice here, next time you pick up a piece of Swiss cheese, you'll never look at it again in the same way. But what you'll see is you've got all these holes. This has got very high porosity. This is probably on the order of about 40%. But you notice that if you look between them, there's no connection between those holes. So the fluid that's in there is just going to sit there and you can't get it out. Now in Alberta, in oil and gas country, if they run into a rock like this, they have an answer for it. They call it fracking. And what they do is actually put explosive down the hole, blow them up, and that fractures the rock to allow the oil and gas to move and come out. I'm not recommending that you do that here. I'm just letting you know that that's what they do in the oil industry. So porosity, always less than 50%. These measurements are done in highly specialized laboratories. I don't do them in my lab. We send them out to get them done. They're always restricted to cores or hand samples. There are limits to the size of rock they're doing. That's important because if you think imagine you've got this room filled with rock, and I'm going to take one core that's 4 inches in diameter, and I'm going to use that to indicate what's going in the whole room. It may or may not work, but that's what we have to do. These are expensive to do. We can't afford to produce endless numbers. So we've got the permeability of that, but permeability that is measured in the core cannot include fractures, joints, or caves. So if you've got fractures, in fact, they tell you if you're going to send a piece of core for analysis, it cannot have a fracture that goes right through it, because the testing won't work. But if you think about it, that fracture is like a highway for water. So water can just flow through it. And this is where we have some problems to deal with. One of the strange features on the Cayman Islands, and I still can't explain it, I can't even come close, is that the vertical permeability here is always less than the horizontal permeability. It's bizarre, and I cannot explain it. We don't see that in other successions elsewhere. If somebody can ever come up with an answer for it, I'd like to know what it is. So let's have a look at some examples of, give you an idea. Go back to the east end of Cayman Brac, complex cave system, huge porosity. You can see that. We imagine we drilled a core and got core from it, come down here, we get core here, but nothing here. So you can't get a measurement. If we came here, we could drill that whole thing and not even have any knowledge of all these caves. So it's a somewhat hit and miss type situation. There are other things they can do, but we have not been able to get it very expensive to do other things. That porosity is of all sizes. I've shown you the cave, but at the other end of the spectrum, notice the scale bar here, 0.5 millimeters. And some of these holes in here are less than that, but collectively they are important. And those can be great storage places for the fluids that we're looking at. Fractures, if you go on the northeast corner of Cayman Brac, you can see fractures cutting down the entire cliff face. This is like a highway for water to go in. So there's a lot of water moving through these. On the east end, west end of Cayman Brac, there's the splits. This is a joint system that's opened up. This is about 2 meters wide. You can stand there and watch the water go up and down as the tide goes up and down, telling you that even though you're in the middle of the island, it's connected to the open ocean. And we can, using air photographs and satellite maps, we can, on this island, map all these joints and fracture systems. And what I want you to imagine is that this is where the seawater can come in and flows inland into these rocks. A picture I want to paint for you is that in the subsurface, the water doesn't just sit there, it's moving all the time. In the case of the Lower Valley Well, things worked out nicely. It's just so that we've got a full sequence there, Pedro Castle Formation, the Cayman Formation, Brac Formation. It just so happened by luck that at the top of the Cayman Formation here, there was a layer of dolostone. It was hard, low porosity, low permeability. And you remember that one of the criteria that we were given is that you could not damage the freshwater lens. So here we had a natural barrier that separated the water down here from the freshwater lens here. Look at some of the porosities here, up to 50, all of these around 40%. High porosities, variable permeability. After all of this work, the abstraction zone was put here, the disposal zone was put here. So abstraction, you're taking out the groundwater, processing it, desalinization. That highly salty water is put back down into the rock. You can do that. It'll still eventually probably make its way out back in the ocean, but it's going to take time. And as it goes through the rock, it's going to mix gradually with the rest of the water there and get itself back down to low salinity. And that's why you can do that. Statistics for the Lower Valley Well, 1998, 3,750 cubic meters per day abstraction, produced 1,500 cubic meters a day of drinking water. 1999, 10,000 cubic meters a day. So you can see that this has been extremely productive site. It's still operating today, still behaving itself. When I say behaving itself, I'm saying that from a geological perspective, okay? Because there's always mechanical issues and everything else. But geologically, if it wasn't working geologically, I would not be allowed back on the island. So I've got a slide at the end that says concluding remarks, and it's blank. Computer gremlins have struck. Everywhere I've gone this week, I've lectured in schools and everywhere. Every single place I've gone, we've run into different problems with computers, so I apologize. But basically, I'll sum it up. Next time you drink that glass of water that you've got from your tap, think about it. Don't just assume that it's there. Look at the work that has gone into producing that. That water has come from wells that have been drilled. It goes through the desalinization plant. Water authority then pipes it to your house and you drink it. Probably never really thought of that before. You just take the water naturally being it. With the ever-increasing population on the islands, there's got to be more of these plants done and more production. They cannot sustain giving drinking water to everybody based on what is available now. So it's an ongoing process. And one of the complications that we run into is when you look at those geology maps I showed you, you get the impression that these vast areas formed of the same formation, so surely it should behave itself in the same way throughout its lateral extent and vertical. Not true. Not on this island. We always run into problems. So some areas will behave nicely, other areas you just sit there and go, I give up. I hope But tonight, and thank you for your attention, I hope tonight I've given you some insights into what we do as geologists and hopefully how it's helped you in the Cayman Islands with the water recovery. I've tried to keep terminology simple. Geology is a nightmare of terminology. We typically have about 6 terms for every single thing, just to cause confusion. So I hope I managed to explain it so at least you've learned something from it. Next time you drink a glass of water tomorrow, think about it. Thank you.